All right, if you're just now watching, we started off talking about sequences, and you can ask me about the opening part. Where we're at now, we just talked about arithmetic and geometric sequences, and now we're talking about why these aren't arithmetic or geometric. The second sequence down here, 4, 10, 28, 82, 3 to the n plus 1. Well, 3 to the n, that looks a lot like a geometric, right? If we just had 3 to the n, that would have been 3, 9, 27, 81. That would have been fine. Yeah. What's the problem with 3 to the n plus 1? Yeah, well, they're being multiplied, but it's multiplied and then add. So is that a common multiple across? Yeah, multiplying by 3 and then adding 1 is not the same thing as just multiplying by 3. And as the numbers get larger, that plus 1 kind of modifies, so it's not a similar ratio. And then, of course, the other one is 2n minus 1. 2n minus 1, that is definitely what type of a sequence? This is arithmetic, right? What about 3n plus 1? Can I take an arithmetic divided by an arithmetic and call it an arithmetic? No. Absolutely not. No, we don't have any crazy names for those, okay? But there are sequences that exist that are outside of those, and that is okay. So the reason why we're talking about this is one of the more interesting applications is what happens if we allow these sequences to go to infinity. Okay? And what we want to decide is if I let the sequence go through to infinity, will it converge? Okay, will it meet a specific number as we take the limit? Or will the sequence diverge? And realize that diverge just means that it doesn't approach a finite value. Doesn't necessarily mean that it goes to infinity or negative infinity. And we'll look at some examples where it doesn't actually grow or doesn't decay to infinity or negative infinity. It actually just kind of bounces back and forth between some numbers, and it gets really weird. All right, determine whether each sequence converges or diverges. If it converges, find its limit. So let's take a look at the first one. 1, 1/2, 1/4, 1/8, or 1/2 to the n minus 1. And you'll notice what this is saying is that there's an infinite number of terms here. This is what we're going to lovingly call a general term. That term can be used to find any of the terms along the sequence. And then after giving you the general term, I actually show that that goes on for an infinite number of terms. I don't know why I put an apostrophe there. Okay? So to determine whether a sequence converges, I need to take a limit. And I need to evaluate that limit as the limit goes to infinity for n. What is the limit as n goes to infinity of 1/2 to the n minus 1? And if you're not sure, it does look like it keeps getting smaller. One of the things that we can do is we can always modify by taking the numerator and the denominator. What happens to 1 as n goes to 1 to the n minus 1 as n goes to infinity? That's just 1, right? What about the denominator? What will that go to? Gets big, keeps going, right? So I have 1 to the n minus 1 over 2 to the n minus 1. That will eventually go to 0. We say that that converges to 0. Yes, Mr. Adams? I did. I do not have anybody at this point in time. No, not this year. No problem, man. I appreciate it. Yep. Yeah, it was recording right there. All right. So we say that this converges to 0. The sequence converges to 0. Cool. That wasn't bad. What about the next one? Limit n goes to infinity of -1 over 2 to the n minus 1. Now, it might be useful to try to break this down and figure out how I would break down that particular problem. Where do you think I want to lump the negative in? I could put in. I usually like to put the negative actually with the 1 because I would prefer the negative to not actually change the numeric value. I want the negative to just be a sign change. So what you'll see is even if there's not a 1 in the problem, I will usually create a multiple of negative 1 and let that n go to infinity. We take a look at this. Negative 1 to the n minus 1, what does that do? Yeah, plus, minus, plus, minus, plus, minus, plus, minus, just bounces, right? What about 2 to the n minus 1? Gets really big. So it doesn't matter that that goes plus, minus, plus, minus, plus, minus. No, just goes to something, some version of 1 over infinity. We say that that converges to 0. What I'd like you to look at is as you look at these terms, do you notice that these, what is the connector between each one of those terms? They're all being multiplied by 1/2. And the second line, they're all being multiplied by? If I were to write out a bunch of terms in this sequence, this would be what? 3/5. The next term would be 9/25. The next term would be 81 1/25. Anybody want to take on the next one? 243 625. That's going to keep going, right? Correct. But when I look at that term, if I look at those terms and I take the limit as n goes to infinity of 3 over 5 to the nth power, well, that's really the limit as n goes to infinity of 3 to the n over 5 to the n. Now this is a little bit tougher because 3 to the n goes to what? What about 5 to the n? All right, so we either have to figure out how to deal with that or we have to logic our way through it. Doesn't 5 to the infinity get a whole lot bigger than 3 to the infinity? I mean, just look at the rate. After 4 terms, I only made it up to 243. But in the bottom term, I made it up to 625. If we start getting even larger, we get up to the 10th term. It's going to be a big difference. This actually goes to, forgot to put converges to, and then I didn't put a 0. So we can say that this converges to 0. In fact, if you look at all 3 of those, what can you tell me about the absolute value of the number inside of the parentheses? We're going to call that an R. This is R, this is R, this is R. What can you tell me about all 3 of these R's? The absolute value of those are all less than 1. And in each one of those cases, what have you noticed? They all converge to 0. That's true for any geometric sequence. Not that we really need a shortcut on those. It's not like they're particularly difficult. What about the next one? The next problem is the same exact concept, except now what have I done with the rate? Flipped it. Now if we let limit as n goes to infinity, we've got 5 to the n over 3 to the n. That 5 is still going to grow faster, which means that we're going to get infinite growth. This diverges. If that absolute value of r is bigger than 1, you get something that diverges. And what you may want to put is that this is just unbounded growth. Here we can say unbounded growth. Unbounded growth is probably the easiest out of all of the problems that we're going to deal with. Unbounded growth is fairly simple to see. But that is not the only thing that could happen. You should know. Turn the page. The first one's going to be a trig question. So let's look at this. A of n is defined as sine of n. So just so you can kind of get an idea of what we're looking at, that's sine of 1, sine of 2, sine of 3, sine of 4, and so on and so forth for all eternity. Sine of 5, sine of 6, sine of 7, sine of 8, sine of 9, sine of 10, yada, yada, yada. Limit as n approaches infinity of the sine of n. What do you notice? What do you know about sine function? Starts at 0, comes up, goes down, goes down, goes down, goes down, goes up. So what happens? It doesn't cancel. This does not approach a value. Remember, we're going to let this n go to infinity, which means this is going to continue going, right? Yes. As that n continues to grow, all the function does is oscillates. Diverges, and we can say that there is an oscillation. Should. And the difference is that in the functions that we're used to looking at, we play connect the dots. That is the graph that we're looking at. We're looking at just the individual dots now. We're not going to play connect the dots. What about the next problem? A of n is equal to 3n plus 2 over 5n minus 1. This is no longer a... I realized, I was like, I wonder if I have my mic on. That would have been terrible. I do. That limit's pretty easy. We should see same power, 3/5. Converge or diverge? Converges. Remember, I don't have to converge to 0. I can converge to 3 over 5. That's fine. We're good with that. Okay. A of n is equal to 3 plus negative 1 to the nth power. Let's because if I do this, I have no clue what on earth is going on, right? Maybe you do. I don't. Let's write some terms. When the n is 1, this is 3 plus negative 1 to the 1. What is that going to give us? Okay, the next one would be 3 plus negative 1 to the 2. Next one is 3 plus negative 1 to the 3rd. 3 plus negative 2 to the 4th. So, what do we say? Diverges, oscillation. Cool. Natural log of n where'd you get x? Before you can use L'Hopital's, you have to prove to me what? You have to show me that the limit is, you have to show me the limit as n approaches infinity for natural log is infinity. You have to show me that the limit as n approaches infinity for n is infinity, and then you can do L'Hopital's rule. No, I just know the rules. Huh? It's actually really easy to tell if you know what a natural log function looks like compared to a linear function.
Doesn't it go like
Natural log? X.
Oh wow, they don't touch.
Which one grows faster?
The X.
By how much?
A lot.
Does it matter how, when I get to large numbers, does natural log matter?
No.
That's all I need to know, folks. And that's something that you're expected to know. Eventually, natural log becomes so ridiculously small that even though it will approach infinity, it never equals infinity. It never will play anything close to just n. We say that this converges to 0. And if you're struggling with that, you're screwed. And I don't mean to be mean about that. It's the truth. You will not survive this you will not survive this upcoming section if you do not see that. If you do not know that the natural log of n over n goes to 0, and you don't know that natural log grows slower than a linear function, this next section will be nearly impossible for you, because that's basic knowledge you're expected to have. Okay, last one. A sub n is equal to n plus 1 over n plus 3.
Oh, you have an exclamation point.
Okay, so what? Remind me what these factorials are. Easier to remember it backwards. So if it's 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. Right idea, but if we conceptually we want to work it backwards, and the reason why is that this is kind of hard to see whether it converges or diverges. All right, just to be able to look at that, does n plus 3 really wind up with that much larger of a value? So what we want to do is we want to make sure that we can remember how to manipulate a factorial. N plus 1, we're going to leave as n plus 1. N plus 3, though, because that's n plus 3, I can modify that. Because n plus 3 is my first multiple, isn't it?
Yes.
What would be my next multiple? What's my next multiple? Those will reduce. 1 over n plus 3 times n plus 2. We say that converges to 0. That's an introduction to these. What I would like to do actually next is there is another, go to the next page. So what that is sequences. That is all review. That is stuff that we should have seen at this point in time. What comes next is the more interesting stuff. Okay? The next set of things that we're going to, oh my goodness, where did that paper go? I had a paper, they had a bunch of numbers on it. Oh well. That makes me sad. Anyways, on the next paper, what we are going to look at is we want to take a look at a concept called a series. So, a sequence is the infinite number of terms that exist, okay? It's the actual discrete number of terms. Apparently I'm going to need to take one of these because I don't know where the other sheet went. A series is the summation of an infinite number of terms. So we're going to add together an infinite number of terms. Or rather, we're going to find out if we add those infinite number of terms together, will that give us an actual value, or will that simply diverge? That's what we're really interested in. That's where we're going to be going over these next couple days. We'll be looking, or a couple weeks, we'll be looking at a series of different tests to prove whether a series converges or diverges. And then what will happen is that will get applied into a calculus setting. But we got to do this part before we do the calculus piece. So we go through, what does it mean? Again, if we converge, the concept is this. If I take what's called a partial sum, okay, and you can see in the first problem down here, given the series, and I show you that I'm going to add together from 1 to infinity. I believe I said 2n minus 1. Okay, so if I take plus 1, thank you. If I add together that series, this becomes a series because 2n plus 1 from 1 to infinity, that would be a sequence, right? And now when I sum it, now I'm taking that sequence and I'm creating a series. That gives us terms like 3, 5, 7, 9, 11, 13, and so on and so forth. When I ask you to find these partial sums then, and I write S of 1, S of 2, S of 3, S of 4, S of 5, what I'm asking you to do is I'm asking you to find, an S of 1 says, find the partial sum of one term from the series, which is 3. The partial sum for 2 terms, 8. It's the 3 plus the 5, right? The partial sum for the 3 series, the 3 plus the 5 plus the 8. The partial sum for the 4, 24. It's the 3 plus the 5 plus the 8 plus the... Hold on, how did I get 8? That should be a 7. Holy mackerel. 9. There we go. 35, that should be the 3 plus the 5 plus the 7 plus the 9 plus the 11. So if I wanted to do a 6, a 7, an 8, a 9, a 10, we could see that we just keep adding on one more term every single time. Now take a look at these partial sums. The partial sum of 3, the partial sum of 8, the partial sum of partial sum of 1 is 3, 2 is 8, 3 is 15, 4 is 24, 5 is 35. What do you notice about these numbers? Converge or diverge? Why do you think they diverge? Yeah. And does it make sense that if I add a 6th, that will increase by an even larger value, and then a larger value, and then a larger value? So take a look. What do you notice? Hey, look, this looks like it's diverging because the distance between each one of these sums keeps growing, right? So when we look, this will probably diverge. In fact, it does. The question is, can you think of any arithmetic sequences that would converge then? But if it's 0.01, 0.001, 0.0001, those terms don't have a constant difference. Those terms have a constant ratio. I want a constant difference, so it could be like 0.2 between each term, but it would be a difference of 0.2 and then another 0.2 and then another 0.2. What's going to happen is that each one of those terms always gets a little bit larger. Or we could go into negatives and they'll get smaller, but then eventually we'll cross past 0 and start getting a magnitude that's larger again, right? So no matter what we do, this arithmetic sequence, an arithmetic series, will also never converge. Juxtapose that with the next one. And I'm going to rewrite that a little bit because I don't like the way it's written. I like to write these out with the power multiplying something like that. And you can see I give you a whole bunch of terms. I give you 10 terms. Using your calculator, I would like to know the first 10 partial sums of this series. I'll do the hard one. No problem. I'm glad to take one for the team. So the first term in this is 1.5. Huh? You're not going to put in. You're going to have to keep going. Plus, blah, blah, blah. Plus, blah, blah, blah. So what's the second term? Was it 1.75? 2.5? 2.25? Fantastic.
Because like it's 1.5 plus 0.75.
Yep. Okay, that's not bad. Keep it to 3 decimal points. For sure? Yeah, that sounds right. Okay. Okay. I know what the last one is. Now look at those terms. What do you notice about those partial sums? It definitely looked like they converged to something. Looks like it converges to 3, right? You know, it keeps thinking it might approach 3. It's not sure. It's always wanted to ask it out on a date. Just never got the guts up to do it. This will, in fact, at some point in time, converge to 3. All right? And we're going to prove that in just a minute. But what you should hopefully notice is that each one of those terms, the distance between those terms keeps getting a little bit smaller. That makes sense. Look at the fractions. The fractions continue to get smaller and smaller and smaller as you go through each one of these terms. One of the issues that we want to talk about real fast is we do want to talk about errors, because a partial sum is going to have an error, which is the actual minus the approximation. In this case, if our actual were 3 and our biggest approximation S of 10 was 2.997, we would be within 3/1000ths of what we want. We're going to do that calculation a lot. We're going to do a lot of error approximating, because the whole point of series and sequences oftentimes is not necessarily to get the perfect answer, it's to get the perfect enough answer. I don't have to be correct, I just have to be correct enough. I know, it's kind of nice. All right? How are you going to make that error smaller? Yeah, keep adding more terms, right? Fantastic. So this is a geometric sequence, or a geometric series, rather. It's the addition of a geometric sequence. Do you think all geometric sequences, all arithmetic sequences diverge? Do all geometric sequences converge? Take a look at the next side. We're going to do another series. This series is geometric. How do I know that this series is geometric? Three over 2 to the nth power. It's to the nth power. There's no pluses or minuses built into this question. So this will be a geometric sequence. Now let's take some partial sums. Again, S of 1, that's the hard one. Now we've got 2, 3, 4, and 5. Ah! What is the next partial sum in this particular series? 3.75? Beautiful. 12 point what? And the fifth one? Converge or diverge? Why? Yeah, that's getting bigger, and the difference between each one of these sums is getting bigger, right? So, but wait, let's go back, because we actually talked about this earlier. If we would have taken this particular sequence and assessed this sequence, would this sequence have converged or diverged? Take the limit as n approaches infinity. That's 3 to the n over 2 to the n. We'd go to infinity, right? So it makes sense. Wait, if the sequence keeps getting larger, if I add the pieces together, won't that mean the series will also get? Oh, like it makes sense, right? Versus in the geometric series that converged, when the r was 1/2, we converged. That should not be a surprise. If you take a look in pre-calculus, you should have talked about at some point in time this equation right here, S is equal to A over 1 minus R, where A is your first term and R is your common ratio. If we start at 1, we saw that this was 3/2 plus 3/4 plus 3/8 plus 3/16, and so on, right? So our first term in this particular problem would have been 3/2. And what are we multiplying each one of these terms by? 1/2. Well, what's 1 minus 1/2? What's 3/2 divided by 1/2? Congratulations, you've just added an infinite number of terms together. What you've just done right there is dealt with a geometric series. By the way, circle that equation. That is the only time I will ever ask you what is the actual value of a series. All right? Unlike in other calculus classes, this is one of the few things where on the actual college level class you may have to do a couple more series additions. In this class, you need to be able to tell me whether a geometric series converges or diverges, and also be able to tell me what it converges to. All right? This is introductory stuff. This is stuff that you should have seen at some point in time, so it's nothing new. All right? Now look underneath. That was pre-calculus. What you see down below, I'm going to tell you to cross off some of these. Telescoping series. We're going to look at it. That's not something you have to have memorized. Root test. That's it. You are going to learn, memorize, and be able to identify every single one of those tests. You're going to look at a series, and you're going to say, I can do this series using a p-series test. And you're going to say, since this hits this condition and this series converges. That is what we will be doing for the next 2 weeks. Then we'll go on and actually use it. This is the deep end of the pool, folks. But it's good swimming. No, you got to get around the whirlpool first at the very end where there's like the giant vortex that'll drag you down. It's good stuff.